Have you ever wondered how a tiny crystal of salt dissolves so easily in water and suddenly starts conducting electricity? What's inside that salt? Well, it's not just sodium and chlorine. It's the result of a powerful chemical interaction known as electrovalent bonding. In electrovalent bonding, atoms do not share electrons. Instead, they completely transfer them. This usually happens when a metallic atom reacts with a nonmetallic atom. Take sodium as an example. It has one electron in its outermost shell and wants to get rid of it to become stable. So sodium atom loses one electron and becomes a positively charged sodium ion. We say sodium gives one electron and becomes sodium positive 1. Now consider chlorine. It has 7 electrons in its outer shell and needs just one more to complete its octet. So chlorine accepts one electron and becomes a negatively charged chloride ion. We say chlorine plus one electron gives chloride negative 1. Now, opposites attract, so the sodium positive 1 ion and the chloride negative 1 ion come together and form sodium chloride. We write this as sodium positive 1 plus chloride negative 1 gives sodium chloride. And just like that, through this full electron transfer and electrostatic attraction, we get a stable ionic compound, the table salt we use every day. Let's look deeper into the nature of this ionic bond. An electrovalent bond is a strong attraction between oppositely charged ions, a cation and an anion. This type of bonding always involves a full transfer of electrons from one atom to another. Take magnesium and oxygen. Magnesium has 2 electrons in its outermost shell and oxygen needs 2 electrons to complete its octet. Magnesium atom loses 2 electrons to become magnesium positive 2, while oxygen gains 2 electrons to become oxide negative 2. So, magnesium positive to plus oxide negative to gives magnesium oxide. This kind of bond forms solid compounds with highly ordered three-dimensional lattice structures. These compounds have very high melting and boiling points, and when dissolved in water or melted, they conduct electricity due to the free movement of ions. So, whether it's the salt on your plate or the ceramic tiles in your home, ionic compounds owe their strength and stability to the electrovalent bond. But how do we know how many electrons an atom will lose or gain during bonding? That's where the idea of electrovalency comes in. Electrovalency is the number of electrons donated or accepted by an atom to achieve a stable noble gas configuration. For instance, magnesium has an electronic configuration of 2, 8, 2. It loses 2 electrons and becomes magnesium positive 2, so its electrovalency is plus 2. Oxygen, on the other hand, has an electronic configuration of 2, 6. It gains 2 electrons to become oxide negative 2, so its electrovalency is minus 2. This information helps us write the formulas of ionic compounds. Since both magnesium and oxygen have a valency of 2, one atom of each is enough to balance charges. So magnesium positive 2 plus oxide negative 2 gives magnesium oxide. It's a powerful tool. Using electrovalency, we can predict how atoms will combine in ionic compounds. Let's compare atoms and ions to better understand what happens during electrovalent bonding. Atoms are neutral particles. They have equal numbers of protons and electrons. But when they gain or lose electrons, they become ions, charged particles. A cation is a positively charged ion formed when an atom loses electrons. For example, sodium loses one electron and becomes sodium positive 1. An anion is a negatively charged ion formed when an atom gains electrons. For example, chlorine gains one electron and becomes chloride negative 1. Now here's something interesting. When atoms become ions, they often achieve a full outer shell, what we call the duplet or octet configuration, just like noble gases. So sodium changes from an electronic configuration of 2, 8, 1 to 2, 8 and becomes stable. Chlorine goes from 2, 8, 7 to 2, 8, 8, again fully stable. That's the beauty of ionic bonding. It transforms unstable atoms into stable ions, all through electron transfer. Now, here's where it gets even more interesting. Electrovalent bonding is also a redox reaction. Why? Because one atom loses electrons, that's oxidation, and another gains electrons, that's reduction. Let's revisit sodium and chlorine. Sodium atom gives up one electron, that's oxidation, and becomes sodium positive 1. Chlorine atom accepts that electron, that's reduction, and becomes chloride negative 1. The full reaction reads: to sodium atoms plus 1 chlorine molecule gives 2 units of sodium chloride. Or verbally, to sodium atoms plus 1 molecule of chlorine gas gives 2 units of sodium chloride. Another example is iron reacting with chlorine gas to form ferric chloride. We say 2 atoms of iron plus 3 molecules of chlorine gas gives 2 units of iron trichloride. Here, iron goes from 0 to plus 3. It is oxidized and chlorine is reduced. So every time an ionic compound forms, there's a redox process quietly taking place in the background. Let's look at more examples of ionic reactions from real-world chemistry. One classic reaction is between zinc and copper sulfate. Here, zinc is more reactive than copper, so it displaces copper from the solution. We say zinc solid plus copper sulfate solution gives zinc sulfate solution plus copper metal. What's happening? Zinc is oxidized. It loses 2 electrons and becomes zinc positive 2. Copper positive 2 gains those electrons and becomes copper metal. Another example, iron reacts with chlorine to form ferric chloride. 2 atoms of iron plus 3 molecules of chlorine gas give 2 units of iron trichloride. Again, iron is oxidized, chlorine is reduced. One more, chlorine gas can displace bromine from sodium bromide. So we say, chlorine gas plus 2 units of sodium bromide gives 2 units of sodium chloride plus bromine. Each of these examples shows how electron transfer leads to stable ionic compounds, and how redox and electrovalent bonding are two sides of the same coin. Let's sum up what we've learned. Electrovalent bonding involves a complete transfer of electrons, typically from a metal to a non-metal. The result? One atom becomes a cation and the other an anion, and they attract each other to form a strong electrostatic bond. The number of electrons transferred gives us the electrovalency, which helps us write the chemical formula of the compound. Ionic compounds like sodium chloride, magnesium oxide, and iron chloride are all products of this process. They are hard, crystalline, and have high melting points. They also conduct electricity when molten or in solution. And remember, this is all underpinned by oxidation and reduction. One atom loses electrons, another gains. So, next time you see salt dissolving in water or metal reacting with acid, think of the beautiful electron dance that forms stable electrovalent compounds. I hope this session helped you see how chemistry is more than just balancing equations. It's the hidden force behind the materials in your kitchen, your batteries, and even your bloodstream. I'll see you in the next class with more fascinating reactions and real world connections.